Here's the answers to the multiple choice quiz on periodicity. And as we go through these answers, I'm hoping that we can find some common themes, right? Question 1, which of these would have the highest second ionization energy? Good AP level question, because you wouldn't have done this last year. Last year you probably just talked about first ionization energy. Now we want to know which of these atoms would require the most energy to remove the second electron. And it would end up being sodium. Sometimes I think kind of mapping out the electron structure helps, writing out the electron configuration, sometimes maybe an orbital diagram. We can lose one electron from sodium. Gladly, we'll lose the first electron, but we don't want to lose the second. The second electron would be part of the core. The core electrons being all the inner electrons in full orbitals, the energy levels are full. I do not want to lose the second electron from sodium. Question 2. Consider the following orderings, which gives a correct trend in ionization energy. Check all that apply. These suck, right? Okay, so let's see where these elements are coming from. On a periodic table, aluminum, silicon, phosphorus, chlorine are going across the third energy level. They're kind of going across the P block. So this is going to be a period trend. When I go across, I'm adding more protons, more electrons. I'm just filling the given energy level. But as I fill the energy level with another electron, I'm also putting another proton in the nucleus. And the extra proton and electron cause a stronger attraction. So yeah, by the time I go across to chlorine with 17 protons and 17 electrons versus aluminum with 13 protons and 13 electrons, chlorine's got the stronger attraction. It's going to take more energy to remove the electron. Beryllium, magnesium, calcium, strontium, this is a group trend. So these are elements that are in the same group going up and down. But as I go down a group, the atoms are getting larger by radius. We're putting electrons in higher energy levels. Beryllium with electrons in 2 energy levels. Strontium with electrons in 5 energy levels. But when the electrons are really far from the nucleus, that attractive force should be weaker. And so it should take less energy to remove the electrons from strontium. More energy to remove the electrons from beryllium. That one's backwards. The third one is a correct group trend. Iodine, bromine, chlorine, and fluorine are all in the halogen group. And then, yeah, with fluorine having electrons only in 2 energy levels, iodine in 5 energy levels, fluorine should require the most ionization energy. The electrons are closest to the positive nucleus, so they'll experience the strongest attraction. And then finally, that last one is correct. Sometimes people get this one a little bit goofy, but when you see a list of ions, just double check to see if they're isoelectric, because again, that would be like an AP thing that we wouldn't have done last year. Now, if they would have just given me like all the halogens as -1 ions, well, then they would just follow the same trend as they would in a group if they were the normal atom. As long as it was a group trend and they all form +2 ions, or they all form their -1 ion. These elements, oxygen, fluorine, sodium, magnesium, they are not in a group together, and they all have different charges, which is kind of like a red flag that this could be an isoelectric series, just meaning that they'll all have the same number of electrons when I take the charge into consideration. So yeah, if oxygen gains 2 electrons, it's going to have 10, and then same thing with magnesium on the opposite end. Normally 12 electrons, but if I lose 2, I got 10. So they all have the same number of electrons. They're all going to have the same electron structure. But with magnesium having the most protons, you've got the greatest nuclear charge. You've got the most positively charged nucleus. That creates the strongest attraction for those 10 electrons. And so not only then would the radius be a little bit smaller, but it's going to take more energy to remove an electron. Love it. Number 3 was fine. Which of the following shows the correct order for increasing radius and ionization energy, respectively, in that order? So here's kind of where these elements would fall on the periodic table. If I'm going increasing radius, well, yeah, the sulfur should have the highest radius. It's got electrons distributed amongst 3 energy levels. Oxygen and fluorine, only 2 energy levels. But then between oxygen and fluorine's got an extra proton, an extra electron. That's going to create a stronger Coulombic attraction, right? When the charges are stronger. And so fluorine's going to be a little bit smaller. And so my trend would be fluorine the smallest, then oxygen, and then sulfur the largest, with electrons and more energy levels. The opposite then would be true of increasing ionization energy. So if sulfur atoms are the largest by radius, the electrons are farthest from the nucleus, it'll take the least amount of energy to remove the electrons from sulfur. It'll take the most energy to remove the electrons from little baby fluorine. Number 4, they're all true. All of these, especially like these last two, like, yay! Like, these are the way you're going to explain trends, especially period trends when they're going across the periodic table. Yes, neon has a greater ionization energy than boron, and yes, its radius is smaller. But these last two, these are the whys. This is how I'd have to explain it in a free response question. You could say there's a greater Coulombic attraction, meaning that neon has more protons, more electrons, it's got stronger charges, and really the radius, initially is pretty similar between boron and neon, or just filling the second energy level. And yeah, once I get more protons and more electrons, that attractive force gets stronger and the radius shrinks a little bit. But the main reason why these trends exist in ionization energy and radius is because of the stronger attraction. More protons in the nucleus, more electrons in the energy level, or again, you could say greater nuclear charge. That nucleus is becoming more positively charged, so it's more attracted to its electron cloud. Love it. 5. Which of the following best accounts for the fact that the fluorine ion has a smaller radius than the oxygen ion? And yes, they are isoelectric. When I take the charge into consideration, they both have 10 electrons. And so, yep, with the extra proton, fluorine's going to have a stronger attractive force, which creates a smaller radius. And so we'd say greater nuclear charge. Nuclear mass, the mass isn't really what's causing the radius to change, and the radius is affected by like the electron cloud. So yeah, I'm adding an extra proton in fluorine, but it's the attraction between the nucleus and the electron cloud that makes the radius smaller, not the fact that the mass is greater. That would also include neutrons, which have nothing to do with it. More total electrons, nope, they've got the same number of electrons. And yeah, fluorine has a greater electronegativity, but that has to do with gaining electrons and not necessarily affecting the radius. It's the attraction that affects the radius. I think sometimes people get their undies in a bundle when they see the term electron affinity energy, but they get electronegativity. Electronegativity is the ability to attract or steal other electrons. And so we know, like, yeah, fluorine does have the highest electronegativity. It's a really small atom, so there's lots of attraction between the nucleus and its own electrons, maybe even the electrons of a neighboring atom. Combine that with the fact that fluorine already has 7 valence electrons and just needs 1 more to fill the outer energy level. Makes fluorine a dangerous little atom. Okay, so if we get electronegativity, it's the ability to attract and steal electrons. When you do that, when you put the electron in the outer shell, fluorine now has become more stable. stable. The fluorine ion is more stable than the fluorine atom because now we've got the full outer shell. Stable means low energy. So when I gain the electron, energy is released. And so that first one is a good example of an equation that could represent electron affinity energy. It's energy released, it's an exothermic value. Energy released when I gain an electron to form a negative ion. Oh. Now if I were thinking about the opposite is ionization energy, and that might be like the second one. Ionization energy. They're opposites. So electron affinity is energy released when I gain the electron. And again, like the word affinity means that you really like something, if you have an affinity for something. And so yeah, these are going to be elements like fluorine, oxygen, I mean any halogen, sulfur, nitrogen, elements that would want to gain electrons and form negative ions. They become more stable by gaining electrons. We don't usually talk about electron affinity energy with a positive ion like sodium or magnesium because they're just not going to be stable by gaining electrons. Instead, they would like to lose electrons, which requires the input of energy. I have to add energy to remove the electron and form the positive ion. And the electrons are attracted to the nucleus, so if I want to separate them, I'm going to have to add a little energy. So ionization energy and electron affinity energy are just opposites. And electron affinity energy kind of goes hand in hand with electronegativity. I love question 7. This is another good AP level question and we talked about ionization energy in first year chem, but not in this way. So we look at successive ionization energies. Each time we remove an electron, we've got more protons versus electrons, and so we have a more positively charged nucleus in comparison to the negative charge of the electron cloud. Greater nuclear charge causes a stronger attraction. So it always takes more energy each time you remove an electron. But at some point, you're going to find this big gap in ionization energies. And that's always the switch from valence electrons to the core electrons. And so here that big gap comes between the 4th and 5th electron. So we'll lose 4, but we don't want to lose the 5th. So there must be 4 valence electrons. And if I were to lose those 4, it would be a +4 ion. But then the 5th would be a core electron, and it would take a lot of energy to remove a core electron because these are my stable full orbitals. And finally, question 8. There are a couple goofy exceptions to the trend in ionization energy, and this is a real common one, that you would expect the ionization energy of oxygen to be a little bit higher than nitrogen. It's got an extra proton, an extra electron. Attraction should be stronger. But it's actually a little easier to remove an electron from oxygen versus nitrogen. And so when we think about the way the electrons are distributed amongst the orbitals, oxygen's got 2 electrons paired and 2 single. Well, if I'm going to remove an electron, I'm going to probably remove one of the paired electrons. And because they are paired, there's already going to be a little bit of electron repulsion. And so it makes it a little easier to remove one of these electrons from that paired orbital. Having your electrons in single p orbitals like nitrogen is actually kind of stable. And we're looking for, when we get to like p orbitals and d orbitals, we're looking for the orbitals to either be all full, or the second best configuration would be all half full, because then I don't have any repulsion like nitrogen. And so like nitrogen is relatively stable. It would like to gain 3 and fill the orbitals, but as an atom, a neutral atom, it's okay. There's no repulsion. And so yeah, it would actually be a little bit easier to remove an electron from oxygen because there are two paired electrons. And when they're really close to each other, you have a little extra electron repulsion. Yes, oxygen has a greater nuclear charge, but then you would think that if that were the reason for this trend, you would think that the ionization energy would be higher in oxygen. Yeah, oxygen atoms do have a smaller radius, but again, that would, you would think, make the ionization energy higher. The electrons in oxygen are distributed amongst less energy levels. No, they're in the same energy level. It's the repulsion. There. So hopefully there's some common themes that we're always thinking about the attraction between the nucleus and the electron cloud. Is it a strong attraction, a weak attraction? That's going to affect all the trends. Radius, ionization energy, electron affinity energy, and electronegativity.